Greetings, Algebra.
On this beautiful day, we are going to be graphing and analyzing transformations of quadratic functions. So your goal, first off, is to scan this QR code or click the link on my website, and you're going to run through here and see what happens to the parent function, which is f of x equals x squared, when you adjust things here. So run through that and make sure to fill in all these gaps. Feel free to work with a neighbor on that. And now you've gone through and finished the conjectures. Now I'm going to formalize it real quick here to show you what it looks like in this form here. By the way, this has a name. This is called the vertex form. Vertex form. And you might recall, of course, that when we have linear equations or linear functions, let me clarify that, linear functions, we have a couple different forms. We had standard form, and you don't need to write this down. We're just reviewing. Standard form equals C. We also have slope-intercept form. Tell me y equals mx plus b. So we've got different forms. We even have this form, which is called point slope form, and then m times x minus x1. So we've got a couple different forms, and they each have their own benefit. Well, the same thing here for quadratic functions. We have different forms, and the first form we're going to look at is this right here, called vertex form. So we have a times x minus h quantity squared plus x. This looks very familiar because it also shows us, if we remember, absolute value function. And the absolute value function looked like this. Y equals a absolute value of x minus h plus k on the outside. So this looks virtually the same. Notice the major difference though. This one has absolute value and this one has square, but the a, the h, and the k are the same. In fact, the h inside has that negative attached to it, which is important. So first off, the parent function. And as I just identified there, the parent function is just the square part. So y equals x squared is the parent function. It's the function that defines the shape. And what shape is this? We're going to specifically call it a parabola, but some will call it U-shaped. All right, domain. What is domain and range? Of course, domain is what values of x am I legitimately allowed to put into the function. So we ask that question, what numbers am I allowed to square on the number line? What can I square? And the answer is everything. I can square everything. So my domain is all real numbers because there's no restriction on squaring. However, the range is very important. Notice the numbers that I get out will always go in a particular direction. In this case, I only get positive numbers and 0. So how do we determine what my range is? The key is actually the the k. The k is my range. So y is either greater than or equal to k, or y is less than or equal to k. When? That's actually important to tell, depending on which direction it opens, which we'll get to in just a second. All right, we recall, of course, our friend h, and notice that h is there without, don't include that negative, it's the opposite of what I see. So h is how much we shift left or right. So it's a horizontal shift. The k is also a shift, but it's my vertical shift up and down here. And hk together is called my vertex, as long as it's in that form, h comma k. Axis of symmetry is always based on the h. So x is equal to whatever h is. So notice, axis of symmetry is based on the h, the range is based on the k. So, one thing to point out is that as a gets larger, and notice that I'm taking the absolute value of that, so a is 1, 2, 3, 4, 5, 6, those kinds of numbers. What happens is that it becomes more narrow, or narrower. Well, to flip that around, as when we have numbers like 1/2 or 2/3, or the negatives there as well as the a, so this number in the very, very front, as a is changing, then what happens is we end up getting more wide or wider than the parent function. And the key thing is that if a is negative, it opens down. Opens down. And if a is positive, then the whole parabola opens up. And this brings us, of course, back to here. Our range is dependent on this. If it opens up, then it is going to be y is greater than. Okay, so I'm going to point that out. So as long as a is greater than 0, then it opens upward. And if a is less than 0, then my range is y is less than or equal to k. That's a lot of information. We'll break it down a little bit. Okay, another thing we want to point out is historically, when we were graphing, whether it be slope-intercept form, so for example, y equals 3x plus 2. We wanted to graph that. I'll quickly do this. What we did was we began at 2, so somewhere around here, I'm just estimating. And then, of course, this means go up 3 and then right 1. Then up 3 and then right 1, something like that, and then we connected the dots. And the same was true for absolute value. We did something similar to that. Well, we're going to do something similar to that here, but instead of considering slope, because notice this doesn't go slope like this. Notice what it doesn't do. It doesn't just connect dots with a straight line. It connects dots with a curve. So what we're going to do is show you a pattern that arises. So we're not going to consider slope necessarily, although slope, the idea of slope does show up here. So we're going to look at the nice points. What do I mean by nice points? Well, nice points are the clean points here. 0, 0, 1, 1. Up here is 2, 4, right there. And the next nice point is right here. And then there's actually another nice point a little bit higher at 4, 16. Turns out there are the other slopes, the other nice points on the other side of the axis of symmetry. And the axis of symmetry here is x equals 0. Okay, so we're just going to look at the positive side for now, just to establish a pattern. Of course, there's this one too. All right, so watch the magic here. What happens when I want to get from this point to this point? Well, let's watch the counting. I go up 1, right 1. So if I do the initial slope, it's 1 over 1, which is simply 1. Now let me try that again to get to the next nice point. Up 1, up 2, up 3, and then right 1. So my second slope there is up 3, right 1, which is 3. Let's do the next one. 1, 2, 3, 4, 5, and then right 1. So my third slope is 5 over 1, which is 5. Let's see. 1, 3, 5. Looks like odd numbers to me, so let's try that again with the next one and see what we get. 1, 2, 3, 4, 5, 6, and 7 over and right 1. So the fourth slope here is actually 7 over 1, which is also 7. So notice the pattern that we've just established. The parent function has a pattern that does this. 1, 3, 5, 7, and it keeps going. It would go 9, etc. And I do want to point out to you that every single one of these is always right 1, right 1, right 1, right 1. So that's implied. So let me just show you what happens. To quick graph this, if I know where the vertex is, I go up 1, right 1. Then I go up 3, right 1. Then I go up 5, right 1. And then go, if there's room, up 7, right 1. And then I can go up 9, right 1, etc. So that would be the pattern. And notice what the pattern does too. Everything just reflects to the other side of the axis of symmetry. So that is absolutely key. We're going to remember this parent pattern right here. This parent pattern right here is going to help us establish a quick graph. Before, when we were doing linear, we used this pattern, which is just my slope, but we repeated the 3 up 3, right 1, up 3, right 1, and we never variated, that's not a word. So let's now look at quick graphings. So the parent function y equals x squared has the slope pattern of 1, 3, 5, 7, etc. to get from one point to the next, and x always counts by 1. It's up 1 over right 1, up 3, right 1, up 5, right 1. So always counting by 1 for the x values. Thus, when a is not equal to 1, we need to multiply a by my super pattern, by the 1, 3, 5, 7, etc., in order to get my new pattern. So watch this. This guy here is a 2. So I take that 2 and I multiply from my pattern, the 1, 3, 5 pattern, etc. And so what do I get? I get 2, 6, and 10, etc. Now 2, 6, 10 is quite a bit. That ends up being quite a lot of numbers to count. So I'm not going to go up to the 7, etc. So this first one here, and in fact for all of these, the vertex is going to be 0, 0. In a minute we'll explain why that's the case. So 0, 0. So that means we start right here. Here's my 0, 0. And let's follow the pattern. And remember, each of these patterns are always right 1, and then we're going to reflect. So now what we're going to do is use those patterns, the up to right 1, from here. So going up to right 1 puts me here, and I'm going to reflect that across the axis. Then I do the exact same thing, this time with the 6. Now I go up 6, 1, 2, 3, 4, 5, 6, and right 1, and I'm going to reflect that across the axis. And now let's do the same thing, but with the 10. So I go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and right 1, and I'm going to reflect that across the axis. Now, once we have those, all we need to do is we have to make our curve fit nicely. Notice what we don't want to do is make this curve a line, although it's going to feel linear probably up here because it stretches so far, like that. So there we go. Let's practice some more to see what happens. Like we said, for now we're going to say our vertex is 0, 0 here, and our axis of symmetry is this one right there. We'll practice more of that a little bit later. So I'm going to take this 1/2, and we're going to multiply the 1/2 by my super secret pattern, which is 1, 3, 5, etc. Okay? And this is what we get. Now, pay attention here. We get 1/2, 3/2, 5/2, etc. Now, as I stated before, it is extremely important, just like I did here, that it's always over 1. This pattern part over 1. So watch what I do here. Over 1, which means I go right 1. I go up 1/2 and right 1. This one says I go up 3/2 and right 1. And the same thing here. So just so that you can see the idea, this is 0.5 or 1/2. This is 1.5. This is 2.5. So it's going to feel funny, but we're going to go up by fractions. So let's see here. To go here is up 1. Nope, we're going to go up 1/2. So let's see where we go. We go up to 1/2 and right 1. And then we're going to bounce it. Now, in this case, I went up to the 1/2, but I also went up 1/2. So now I'm going to go up for this guy here. For this one here, I'm going to go up 1.5. So here's a 1/2, and here's a 1. And then I go right 1. Always go with these intervals, always go by 1. Every single time, we always go by 1. That's the point of this pattern. Now let's look at the next one. I'm going to go up 2.5 and right 1. So here's up 1, here's up 2, and here's up 2.5, and I go right 1. Now I'm going to reflect that across to be here. Now I can go ahead and connect the dots. Notice that these points are closer together than the previous one, And since the scales are the same, I'm counting everything by ones. Notice that this is significantly wider than this one. This one's more narrow than the parent function because of that 2. This one is more wide than the parent function because of that 1/2. All right, and let's practice one more. This one is, the a is -3, so this is going to help us out because the a tells me 2 things here. The negative means that the whole function opens downward, and the pattern is I'm going to take the 3 and multiply it by the 1, 3, 5, etc. Notice I'm going to run out of space here quickly. So that's 3, 9, and 15, etc. So, like we stated earlier, our vertex starts here, and our axis of symmetry is still the y-axis, like so. Okay, now to get to the first point, I have to do 3 over 1. But since I'm opening downward, I'm going to go in the downward direction. 1, 2, 3, and then right 1 or left 1. Remember, it actually doesn't matter because they reflect. Now I do 9 over 1. 9, right 1. So down 1, 2, 3, 4, 5, 6, 7, 8, 9, and right 1. And we're going to reflect that across there. Now, I'm running out of space. There's no way I can get 15 out of this next part. So at this point, I can go ahead and try to fit my curve. Let me show you what not to do real quick. Do not do straight like that. Okay, this is not, the whole thing is a nice smooth curve. So use your eraser because sometimes it's going to take 3 or 4 tries to make it look good. And then this one's got to come way down. Try not to do this. Here's another bad thing to do. We like to do this because of the curvature of our hands, the way that we're holding. So I just kind of go slowly sometimes with extra marks just to get the feel. There we go. Now take some time here to graph this one here, and we'll pick this the rest up at a later date.